Okay, so we're back. All right, class. Okay, so apparently the video stopped recording, so here we go from where we left off. This is what we have is delta star is basically the displacement layer, displacement boundary layer, as we talked about, of in terms of how the boundary layer is, the streamlines are deflected by the fact that there is a boundary layer, and so it's the integral here that I'm showing here, and now this is for the exact solution. Excuse me. it's between 0 and infinity. Now I'm going to show you that we only have to really integrate under the brown boundary layer up to delta. But let's go ahead and just to illustrate what I'm talking about, let's go ahead and just do this full integration. We can break this into two integrals. We can go from 0 to the boundary layer, delta, and then we can say that's 1 minus u. This is, let me go ahead and, actually let me go ahead and just change back to the normal pen I had. Alright, so this is 1 minus little u over capital U dy. Now, and then plus the integral from delta to infinity, and then 1 minus little u over capital U dy. Alright, so what we got going here is between 0 to delta, we're going to go ahead and just write what that is. And that's 1 minus, now for u, we're going to replace the function that we have, which is capital U y over delta, and then we have to include the capital U from the integral dy, and we do the same thing between delta and infinity. However, what we do is we say for little u, we basically it's the constant velocity, right? It's actually capital U, which was v. So remember what I said, that this was actually v that's the entrance velocity, which is the same thing as capital U. Now why the problem has that as v, I don't know. They could have just left it as capital U. I don't know why they have to call it capital V. But anyway, so it's basically U over U, which we know that this is going to be 1 minus 1, which is basically 0. So this half of the integration falls off, and we're left with just doing the integration under the boundary layer, under the brown boundary layer. Okay, and so what that looks like, so I'm going to go, just so we have space here, I'm going to go and say this is the integral from 0 to delta. That's delta, and then what we have is 1 dy is basically the it's y. I'm sorry, hold on a second, this is wrong. One second, I jumped ahead here. Well, we can just go ahead, let's just skip the integral. We're just to start doing the integration already, so we can just integrate this here, and when we integrate 1 minus, so we know that this cancels that, and we're just left with y over delta. So this turns out to be, when we integrate y minus y squared over 2, and we can't forget our delta that we have under here. And this is evaluated at the boundary limits of y is equal to 0, y is equal to delta. Right? And so what we're left with, excuse me, what we're left with is we have that, again, delta star, which is the displacement boundary layer, is equal to when we place I'm sorry, hold on a second. when we go ahead and substitute the integral boundary points into into this calculation here, we have this is equal to delta over delta minus delta over 2, which is equal to delta over 2. So I think we needed to find the ratio. So I think the problem asks us to find the delta star over delta. So we can get that from this equation, and we have that that's equal to 1/2, which is equal to 0.500, and that was the answer given for the homework problem. And now for the momentum boundary layer, we do the same thing, we just have a different integral that we have to solve for. Again, we go from 0 to infinity. This time it's u over capital U times 1 minus u over u dy. And so for the same reason as we did, we only need to evaluate from 0 to delta, because from delta to infinity it goes to 0. The integral goes to 0. So we're left with, just as in previous, we're left with integrating between 0 and delta u capital U 1 minus u capital U dy. And if we're going to go ahead and solve for this, this is equal to, when we do the integration, this is equal to y squared over 2 delta, and go ahead, minus y cubed over, hold on, so I don't want to, y cubed over 3 delta squared, evaluated at 0 to delta. And so what that gives us then, when we do the integration, it's equal to delta divided by 2 minus delta divided by 3, which is equal to, so now we have, actually let me do an arrow here, we have that the momentum boundary layer is equal to delta divided by 6. Or we were going to put it in the ratio that we wanted to find, what's the ratio of the momentum boundary layer over the normal or the velocity boundary layer. Basically that is equal to 1 over 6, which is equal to 0.167. And again, that was given in the answer. Alright, so now for the Blasius solution, now we got to, so that's part of the question was to go ahead and calculate those values, those ratios, and now we got to calculate, we compare it to Blasius, right? So I'm going to go ahead and create a new page. So it's Blasius was the person that derived these. So we just went over the exact forms of calculating the displacement boundary layer and the momentum boundary layer. Now Blasius had empirically derived ways of describing the displacement boundary layer. So he has basically delta star over x is equal to 1.72 divided by the square root of the Reynolds number evaluated at x. And so from here you're going to be able to determine what the you're going to be able to solve for the displacement boundary layer directly. So you go ahead and do that. You should have enough information to be able to determine what the Reynolds number is if it wasn't already given. And then he also has an expression for the momentum boundary layer over x, and that is equal to 0.664 over the square root of the Reynolds number. Right, again, we can go ahead and calculate what this is, right? And so once we do that, we can do a comparison. And I don't have the solutions in front of me, but I posted them. Go ahead and you're going to find out that this, I believe that this, I'm not sure, don't quote me if it's true, but I think that this basically is turns out to be about 43% of the exact solution that you derived. And I think this one was something about 21% or so of the exact solution that where you derived the momentum boundary layer. So in other words, I think these were underestimated based on the exact solutions. Now these are great because it's rare that we're always given a function for the velocity distribution for the boundary layer for you, right? I don't know how often you're going to be, or maybe if you can derive that in your work that you're doing, if you're ever doing any highly technical work where you're having to do these integrations, you'll need a function for the velocity distribution. And if you don't have it, then what you do is you can just calculate it directly here. You don't need anything but the Reynolds number to give you an idea or give you at least some number of what the displacement layer is and what the momentum boundary layer are. All right. Okay, that concludes this video. Hopefully this helps, and we'll talk to you later.